All right, picking up where we left off last time, we learned about Lewis structures and how to make them for covalent compounds. We walked through a couple of steps. Also, before we get too far into the lecture, I discovered in the last week that my microphone pops on the recordings, which I didn't know was a thing. So I was shooting myself in the head in Minecraft on whatever day that was that I discovered that, because I was listening through one of my lectures. I've got a new microphone coming in the mail. It should be here soon. So no more crackling, sizzling, popping on the microphone, hopefully. Our steps for covalent compounds for creating Lewis structures, separate from and different from our ionic compound Lewis structures. The first thing that we need to do for covalent compounds, in covalent compounds, everything is bonded together. We can have a bunch of different things that are bonded together. We need to get the correct skeletal structure. We need to get our bones in place for our molecule. This is just going to show relatively where the atoms are. There are usually a couple of different rotations that you can make of the same molecule. Our hydrogen atoms are always going to be at the end because they can form only one bond, and so you can't put them between two things because that would require two bonds. So they're always going to be out on the outside, out on the periphery. They're going to be terminal. They're going to be endpoints. A lot of the time our molecules tend to be symmetrical, meaning if you put a mirror down different lines, you flip the top and the bottom, the right and the left, it should look the same. A lot of the time. Not all the time, but a lot of the time. Once we've got our skeleton laid out, we want to calculate our total number of electrons for our Lewis structure. We're going to sum the valence electrons of each atom in the molecule. So we need to know, anytime we're doing a Lewis structure, we need to be able to look at our periodic table or pull from our memory how many valence electrons does that element have. Remember that valence electrons is the same as the blank A group / column number. So if we have carbon, carbon is in the 14 or 4A column. So it has 4 valence electrons. And every carbon that we have, if we've got 1, we're going to have 4 electrons. If we've got 2 carbons, we're going to have 2 times 4 for 8 electrons. We would count those up for everything that we've got in our molecule. Once we've got the total count of our valence electrons, then we are going to start distributing our electrons among the atoms. We're going to try to give octets or duets to as many things as possible, and the way that we're going to start with that is putting 2 electrons, which is 1 bond, in between every pair of atoms. So all of our hydrogens get 1 bond connecting them with something else, and everything in the middle gets bonds. And remember, we're avoiding triangles. Squares are also bad. Triangles and squares tend to explode. So we're avoiding triangles and squares. Just want to get everything nice and connected. Once we're done with that, we're going to distribute any remaining electrons that we have, and we're going to do that from the outside, working our way inside. So we're going to fill up octets for things on the outside, and then lastly fill up things that are more on the inside that are connected to things. If we're missing some octets, then we can bring in lone pairs of electrons from some of those terminal atoms to make double bonds or even triple bonds as we need to get all of our octets. That doesn't change the number of electrons that we have placed, it just changes who's sharing the electrons. And we did some examples, and for polyatomic ions, we need to remember to include the charge. Electrons are negatively charged. So if we have a 2- charge, that means we have 2 extra electrons. We have 2 electrons more than we would expect. So 2 negative charge means add 2 electrons, for example. If we had a positive charge, that That means that we lost an electron. We've got extra protons compared to our electrons, so we would take off an electron. And for polyatomic ions, we need to make sure that we have a bracket around the whole thing, and then the charge in the upper right corner. In this case, just the example 2- charge that we were talking about. So let's look at an example of a polyatomic ion. We've got Cn, our cyanide ion. For Cn, we've got two things. How can we arrange two things for our skeletal structure? Where do we want to put them? Side by side? Yep, you can kind of just put them anywhere. The one place that I would recommend not putting them is directly on top of each other. Please don't make this more complicated and work in 3D space forward and backward, because that's just plain confusing. So as long as you're not doing this and then trying to draw like lines between them for bonds, you should be good. It's just, you just put them down. There's no wrong way to put them. You can also put them nitrogen first, then carbon. It doesn't matter. I'm putting them Cn because that's what we've got. All right, so that's our skeleton. Now we need our valence electrons. We have a carbon. Carbon has how many valence electrons? It's 4 because it's in the 4th column, or the 4th group. We have a nitrogen. How many does it have? 5 because it's in the column over. Is there anything else? Anything else we need to consider for our number of electrons? An extra valence electron gets us a negative. Yeah, we have a negative charge. Got a 1-, and that's going to be 1 electron. So that gives us a total of 10 valence electrons to work with. How many bonds do we need to draw in to connect these two things? It's the minimum number of lines to connect 2 points. It's just 1. So we'll draw in 1 line. How many electrons are in that 1 bond? 2. So we're going to subtract 2 bonding electrons. We've got 8 remaining electrons. Now we have to place the rest of our 8 remaining electrons. Usually in scenarios like this, I just give them each 4. You can do it like that. We could give them as 2 lone pairs. It doesn't really matter. We're still a work in progress. So now we've got all of our electrons placed. Let's take a peek at our octets. Does carbon have an octet? No. Does nitrogen have an octet? No. They both have basically 2 lone pairs plus a bond, which is 6. An octet is 8, so they each need 2 more, but we've already placed all of our electrons. How can we get them to each have more electrons? More bonds. So we can bring in some bonds. And these single electrons could also potentially be a signal to us that we need more bonds. So if we move in some electrons, our structure updates, and it would look like this. Now do we have octets? We've got 2 in this lone pair, plus 1, that's 3, plus 4 in the double bond. Now we've got 7 electrons each. How can we get more electrons? 1 more bond. And we've got this very conveniently last singular electrons here on the bottom that we can add in. So adding those in. Now we've got carbon triple bonded to nitrogen. They each have a lone pair. The triple bond is 6 electrons. Those 6 electrons count for carbon's octet and for nitrogen's octet. And then additionally, they each have another 2 electrons. So they have their octets, and they're happy. Questions? This is not the final answer. What are we missing? The negative charge. So this is a polyatomic ion. And to show that it's charged, we need our brackets around the whole thing, and we need the minus in the top right corner, that one negative charge. Now are we done? Yes, we're done. That's the complete structure for the cyanide ion. Questions before I turn you loose on your own? Yes?
So adding that negative charge doesn't affect the amount of electrons?
The brackets in the negative charge? No, it doesn't affect the number of electrons. It just lets us know that that whole thing altogether has a 1 negative charge. Without us saying, like, it's specifically on the carbon or it's specifically on the nitrogen, because we don't have those skills yet. Other questions? Okay, I'm going to turn you loose on this one. Write the Lewis structure for this yellow minus ion. All right, it looks like we've mostly got at least some of the steps. A couple of us were missing some electrons, or maybe our octets were a little bit scuffed. So we'll go through it. So we've got Cl and O. Our chlorine is going to have 7 electrons. Our oxygen is going to have 6 electrons. And we need to remember that that 1 negative charge means that we add 1 electron. So we're going to have 14 valence electrons. To get everything all connected, we just need 1 bond to start. So we put in 2 bonding electrons. We've got 12 remaining electrons. We want to distribute the rest of these as pairs, lone pairs. Chlorine can hold 6 more electrons. It's got 2 from the bond. We can add another 2, 4, 6 on to fill out the rest of chlorine's octet. Oxygen can also take 6 more. So minus 6 electrons to chlorine, minus 6 electrons to oxygen. We've got no electrons left. Then we would check our octets. So we look at chlorine. Chlorine has 2 from the bond, 4, 6, 8. So it's got its octet. Oxygen's in the same situation. It's got 8 electrons. So it's also happy. And then the thing we need to remember is that we get these brackets and a minus charge in the top right corner. So this would be our hypochlorite ion. So before we put the dots in, I recommend put the bond, then fill in the rest of the dots. And then if we need to, then we can go to double or triple bonds. Otherwise, what I was seeing with a lot of people is we put in 2 bonds for some reason, and then we were missing one of our pairs of electrons. So some people were getting this. Not this. Some people are getting this. And those have full octets. However, if we look at our total count of electrons, we should have 14 total valence electrons. We've got 2, 4, 6, 8 from lone pairs. And we've got a double bond. How many electrons are in a double bond? 4. 2 bonds, 2 electrons each. So that would only be 12 electrons placed. So we would be missing 2, which is why that doesn't work as a structure. Shoop, shoop. Any questions about the hypochlorite ion Lewis structure? All right, we also have exceptions to the octet rule. Here's an important piece of information for us, perhaps. It is impossible to write good Lewis structures for molecules with odd numbers of electrons. You will almost always end up with an even number of electrons. You will usually, like 99% of the time in this class, have even number of electrons. Your number of electrons will end in 0, 2, 4, 6, or 8. Even numbers of electrons. Otherwise, you end up with one of them only having 7 because it's going to have this lone electron, like in this nitrogen-oxygen compound. Another exception to the octet rule is boron. Boron's a little bit of an oddball. Boron is happy with only 6 electrons. Aluminum will also sometimes do this. Which would be a hextet. Otherwise, duet for hydrogen and octet for basically everything else. We can also have what are called expanded octets. So molecules like FFS, molecules like this and like this can have more than 8 electrons around the central atom in their Lewis structure. So look at our sulfur. Our sulfur has how many bonds? 6 bonds, which is how many electrons? And phosphorus has 5 bonds, which means 10 electrons. So we would call those expanded octets. There is an explanation for why we can do expanded octets for those, and it's essentially just they're bigger. Sulfur and phosphorus both show up in our what row on the periodic table? This tall to ride. Sorry, this row, right? The third row. What orbitals show up for the first time in n equals 3? D's? The d orbitals, right, show up for the first time in n equals 3. And so the reason that sulfur and phosphorus and other things that are in row 3 and below can do expanded octets is because they've got access to those d shell orbitals, and those kind of act like extra pockets where the sulfur, the phosphorus, whatever, can hide, can store away some extra electrons. Otherwise, we do not do expanded octets. Unless specifically told for this class. No expanded octets. I think this works with our lab manual Lewis structure sheet. but I'm not 100% sure. The worksheet that I've used in the past, there's explicitly like an expanded octet section, and in that section we'd use expanded octets. Everywhere else, no expanded octets. No odd electrons, only octets. We also have resonance. And with resonance is sort of like, usually I think we think of it in acoustics, like with sound, like, oh wow, this sound is really, this is a really resonant space. This sounds like somebody could make a really, beautiful TikTok in here, singing, Sienna Spiro or something. And it's got like 12 seconds of reverb in the natural space that they're in. And that's cool. But in Lewis structures, it basically just means that we've got multiple options that we can make for our Lewis structure. For example, with SO2, we actually can get more than one good Lewis structure. What is going to be our best skeleton structure for SO2? What's going to give us the most symmetry? Yeah. It might seem like a bit of a bear to put together, but it's really not that bad. So we're going to put the sulfur in the middle, that way it's got symmetry. And how many electrons do oxygen and sulfur have, valence electrons? 6. We've got 2 oxygens, we've got 1 sulfur, so 12 plus 6, we've got 18 valence electrons. To get everything connected, we just need 2 bonds. 2 bonds is 4 electrons. So we've got 14 remaining electrons. If we're placing them starting from the outside, working our way inside, our oxygens both have 1 bond. How many more electrons can we give each oxygen? We can give them 6 more. They have 2. We can go up to 8. 2 plus what equals 8? It's 6. So we can give them each 6. So that's 12 electrons to our oxygens. And I'm going to use an apostrophe so it doesn't look like osmium. That's going to leave us with 2 electrons. Where can we put those last 2 electrons? What doesn't have a full octet? Sulfur doesn't have a full octet. Sulfur has 2 bonds for 4 electrons, so it can hold those last 2 electrons. And now we've got no electrons left after we do that. Now we need to look at our octets. Our oxygens have octets. They've got 2, 4, 6 electrons from lone pairs plus another 2 in the bond. So both of our oxygens are good. Our sulfur, on the other hand, has 2, 4 from bonds plus another 2 from the lone pair. Sulfur only has 6, it needs 8. How can we get it more electrons? Yeah, we can move some electrons in to form a double bond. Are we going to take it from the left side or the right side? The answer is yes. So in one situation, we take it from the left. In another situation, we take the lone pair of electrons from the right side. And this is going to give us 2 structures. Got our red one here. Boom, double bond on the left. And we've also got double bond on the right version. That looks like this. So our oxygens didn't lose any electrons. They've still got their octets, but sulfur has gained an additional bond in the form of this red bond or in the form of this green bond. And then to show that they're both possible options, we draw a double-headed arrow between them. This is the best that we can do with Lewis theory. Both of these are actually wrong. In reality, it's a combination of the two. It would be some secret hybrid of these two. For Lewis theory, we have to draw both because both shows our resonance. So we need both versions, the original album and Taylor's version. And we also need the double-headed arrow between them. It's also possible to have more than two versions. For example, we could have a DJ Khaled remix. And then we would need an additional set of these double-headed arrows. Questions so far about resonance? All right, so either of those two Lewis structures for SO2 would predict that SO2 contains two different kinds of bonds. They predict one double bond and one single bond. Logan's looking at me funny. If we look at SO2 in nature, we're going to find that both of the bonds are equal. It's going to be more of an intermediate strength. So it's going to be more like 1.5 bond strength. Average of 2, 1 bond. And so this is sort of like with cats. If you take two different breeds of cats, you breed them together, the cat that they produce and that you get out will be some sort of hybrid of the two cats, meow, that you put in. So that's resonance. It's to show us basically the two parents, and then in our brain we get to imagine what the kids would look like, which we probably do sometimes. So again, the bonds are equivalent, and we account for that by using the double-headed arrow. And reality is an intermediate. All right, one for us to try, one for you to try. Please write the Lewis structure for the NO2- ion. You might also know what that's called. And make sure that you include resonance structures. Typically, you won't be told that there's resonance structures, but we just learned it, so I'm telling you.
Last name resonance.
All right. It looks like we mostly got the hang of doing the resonance structures. I saw a lot of people that got to the decision point at least. A couple of us forgot we need to add one because of our negative charge. So remembering that this is an ion, we've got a negative charge there, means we add one electron. Do a smaller circle. So we have to add one electron because of that negative charge. A couple of us were missing that one. But a lot of us, it looked like, got the correct Lewis structure. So doing this super fast so that we just jump to the point. You should have ended up with something that looks like this after all electrons are placed. And we'll scribble in the rest. We should have 18 valence electrons. Funny how that worked out, that we have 18 again. And then from this point, our oxygens have full octets. Our nitrogen is short 2 electrons. Deja vu, anyone? And so then we have a fork in the road, and we take it. That's the wrong button. Can we press the, okay, I did it. Okay, blue team. And green team. So these would be our two options. And because it's an ion, it's negatively charged, we also get to include brackets with the negative charge in the top right corner. So that should be our full and complete structure for the nitrite ion plus resonance structures. Typically, you'll be given things with resonance structures, if they're resonance structures, if I'm remembering correctly. You'll be given stuff that's typically just two resonance structures. You can have things that are what you might consider evil, where they've got like 4, 5, or 6 different resonance structures. Usually you only run into those if you mess up with your Lewis structure. Building off of that, wait, any questions first?
When splitting electrons, do we prioritize like the outer atoms first?
Yeah, so when we're distributing our electrons, we're going to start from the outside and work our way in. That way we don't have to pull electrons from the inside out, because then we might have to make decisions about where we put those double bonds if we do it from the outside in. I don't know that it really matters, but I add from the outside in. So we'd add to the oxygens first, we'd have 2 left over, we'd put those on the nitrogen, and then it's double bond time. There's other ways that you can come up with Lewis structures. You don't necessarily have to use this method, but this method works. To build on top of Lewis structures, now that we're masters of Lewis structures, including resonance structures and ions, we can add on top of this what's sometimes very foolishly and mistakenly called Vesper theory. That's my hot take. Valence shell electron pair repulsion theory. VSEPR, Vesper theory. Notice that the S is before the E, so why would you call it Vesper theory? All right, enough of that. All that this is we're talking about our valence shell. What's our valence shell? What's valence? Outside. So our outside electrons, our highest n number electrons. What's an electron pair?
Like a bond with 2 valence electrons.
A bond, lone pairs could also count. Groups of electrons. And what does repulsion mean? They're like pushed away from each other, right? Like repelling. Or pushing away, to use a different word. All that valence shell electron pair repulsion theory is saying is that our outside groups of electrons, our valence electrons, repel each other. All the different groups that we have on the outside, all the stuff that we made in our Lewis structures, because they're electrons, they're groups of negatively charged electrons, negative charges will repel each other. That's like the basic idea behind valence shell electron pair repulsion theory, or VSEPR theory. And each of these groups counts as one electron group. We can have a lone pair. We can have a single bond. We can have a double bond. We can have a triple bond. Those each count as one electron group. So a triple bond, even though it's 3 pairs of electrons, they're all together in one place, so we count it as one group. So a triple bond is one group. A double bond is also one group, a single bond is also one group, a lone pair is also one group. And the repulsion between the negative charges of these groups determines the geometry of the molecule. The groups spread out as much as possible. So they're going to get as far away from each other as they can, and we're going to learn some possible configurations for that spreading out as much as possible. So we're going to use valence shell electron pair repulsion theory to predict the shapes of molecules, and this is one of my favorite modules because I get to show you shapes. Logan is excited. I was looking at Lewis structures. So we want to predict the shape of CO2, which has this Lewis structure. Our CO2 has two electron groups, thing 1, thing 2. Just two groups on our central atom. We're typically only concerned with the central atom. So two groups on our central atom. What's the furthest away that two things can get from each other? Is it right next to each other? Is it the opposite of right next to each other? Complete opposites of each other, which is an awesome time for me to flex on the class, hit a T-pose, or a farm a little bit up here. So since we have two groups, they're going to get as far away from each other as they can, and the furthest they can get away from each other is on exact opposite sides. And so our actual shape for CO2 is the same as we have it drawn here. The oxygens are on opposite sides. That way these double bonds are as far away from each other as they can be. And this is a linear geometry. It's a line, right? It's just straight across. I also consider things, if it's just two things, like this one that we saw earlier, the hypochlorite ion, I would also consider that to be linear. Some people don't consider that to be linear. I think it's easiest to think of that as being linear. It's 2 points. 2 points is what you need to make a line, so to me that looks like a line. Other people call it something else, and I don't know what they call it. So we've got linear shape. We've also got this H2CO Lewis structure. This is one that we started with, or we looked at pretty early into our last lecture, last week. We have 3 electron groups on our central atom. We've got single bond, double bond, single bond. And so those 3 groups are going to try to spread out as much as possible. We've got 3 groups. And we have this fun word, trigonal, the tri at the front meaning 3, and I believe gonal, that ending means points. And planar means that it's flat. Like a plane in, I'll just say math. So the furthest that those can get away from each other, 3 groups, is this Y shape. If you've ever done the YMCA dance, it's the Y shape, but your feet are together. So between my arm groups, we've got about 120 degrees. Between my legs and my arms, I also have 120 degrees. You could also rotate me, but if you rotate me, then I fall over, and I don't like falling over in class. Found a fluff ball on my shoe. Shout out the dog. My actual animal dog, not like a friend. Okay, so first shape, linear. Second shape, trigonal, having 3 groups on it, the tri meaning 3 groups, and it's planar, meaning that it's flat. We're specifying that it's planar because there's another option for trigonal. It's not always going to be flat, but for now it is. We can also predict the shape of methane CH4. There are 4 electron groups, 4 single bonds. Craziest 4 I've ever done. 4 bonds, 4 groups. The furthest that 4 things can get away from each other, you might think that it's square planar. They're 90 degrees from each other. You would be wrong because we live in a 3-dimensional world. So these can actually get further away from each other if we rotate 90 degrees with 2 of those groups. So you're going to hit this X pose, and then you're going to rotate 90 degrees. You can rotate to the right or to the left. We're getting a little yoga in here. And then these top groups can actually come a little further away from each other, and the bottom groups can also go a little further away from each other. And that's how we can get further than 90 degrees from each other. And we call this tetrahedral geometry. What does the tetra prefix mean? 4, and the hedral part means sides or faces. And the bond angle, because of that 90-degree turn at the waist, is now 109.5 degrees instead of 90 degrees. So they're a little bit further away from each other by doing that rotation in 3D space. A tetrahedron is a geometric shape with 4 triangular faces. So if you were to connect these faces and fill them in, those would be the 2 visible faces. This is the same shape as a D4, a 4-sided die. It's the same sort of damage you'd take if you got hit with a cantrip. Some people play D&D. Baldur's Gate 3. Cast that all day. So that's tetrahedral, that's our 4-sided shape. We have more shapes. But before we talk about the extra shapes, we need to explain some new terms. If we look at the shape for NH3, there it is, that's NH3. It's got 1, 2, 3, 4 electron groups. And so its electron geometry, the shape of the electron groups, is tetrahedral. Hits the X, does the 90 degrees. This is the shape of the electrons, the electron groups. One of those groups is a lone pair. Lone pairs don't take up space. Right? It's just electrons. So we get rid of one of those lone pairs, one of our 4 groups, and now we've got how many groups? 3 groups. So 3, trigonal. Is this flat? Is this in a 2-dimensional plane? It's not. I've got one arm sticking out at an angle. It's repelled by this electron group that we got rid of. It's still there, it just doesn't take up space. And so this is still trigonal, but instead of being planar, it's pyramidal. So the arrangement of the atoms is the molecular geometry. This is what we would actually be able to look at, what we would be able to see. And so it's a pyramid shape, not flat. The pyramid's famously not flat. It doesn't really look like a pyramid shape when I do it, unless, right, pyramid. Pyramid. All right. I think some of you are getting why this is one of my favorite lectures. It's incredibly goofy. I also encourage you, recommend do these poses. I'm not joking. I think that it will help you if you actually hit these poses. Of course, you may want to do them in the privacy of your own home, but nobody's done it yet. I have actually encouraged people to do it on exams, and nobody's done it yet. Yeah. So when you're actually like going through hitting these poses, you're connecting your body's shape with hopefully the terms. You're not just doing the body stuff. You're also thinking about what is this shape that I'm making. And so I think that'll help you retain the information. Another shape, if we do H2O, H2O has 4 electron groups. It's got 2 bonds. It's got 2 lone pairs. Its electron geometry is going to be tetrahedral. Here we go again. Tetrahedral. All right, 4 groups. We're hitting our D4 shape. 2 of those groups are lone pairs, and so we get rid of them. And then what would the shape of my legs be? Am I doing the splits? Dang, nobody can lie and just say that I'm doing the splits. Okay, no, I'm not doing the splits. I haven't gotten there yet. So my legs are just bent. They're not quite flat all the way, so they wouldn't be linear. They're bent at a slight angle. The molecular geometry is bent. So these 2 lone pairs are forcing the hydrogens to bend out of being linear. They're bent away from the lone pairs. And so we can get bent molecular geometry. We can also get bent molecular geometry with 3 electron groups when one is a lone pair. I will use, what is the thing that we use? Is it A as the middle? Looking up a specific notation that it doesn't matter. Let's say that A is our central atom, and I'm going to swap that top one for LP. So we've got a lone pair up here. X is just whatever. So if this lone pair is a lone pair, that's going to force these 2 actual groups out of the plane. So it's not going to be linear. It's also going to be bent. So that's the other way that we can get bent molecular geometry. We also have a summary table in our book, table 7.7.1. There's probably other versions that you can find out there. The way that we read this table, if you don't want to memorize the shapes, we would find the number of electron groups on our central atom in this left column. We either have 2, 3, or 4. Then we find, okay, how many bonding groups do we have? How many bonds? How many lone pairs do we have? And we find the distribution that works for us. So like the previous slide, if we have 3 electron groups on our central atom, and 2 of these are bonding groups, and 1 is lone pairs, our electron geometry, the shape of all of the electron groups, is going to be trigonal planar. It'll be the YMCA, or it'll be with our legs spread apart and looking like we're about to dive into a pool. Hands together at the top, like we just high-fived ourselves maybe. But the molecular shape would be bent. We get rid of one of those groups. So our trigonal planar shape and then our bent shape would look something like that. Questions on reading the table or on any of our 5 shapes? There are more shapes. but we're not going to talk about them in Chem 20. You'll learn them if you take Chem 1. So if we want to predict geometry using our valence shell electron pair repulsion theory, our first step, draw the correct Lewis structure. This, within it, has multiple steps. Right, we have to come up with the skeleton. We have to count up all of our valence electrons. We've got to distribute our bonds, distribute the rest of the electrons, do any double or triple bonds. Maybe we also do brackets with a charge. Maybe we do resonance structures. Once we're there, once we've got the Lewis structure, or if we were kindly given the Lewis structure, we determine how many electron groups do we have on the central atom. Our options are 1, 2, 3, or 4. Those are the only numbers that we're going to see. If it's just 1, it has to be linear. So number of electron groups on our central atom. Then we want to determine how many of those are bonding groups, how many of them are lone pairs. You can either have memorized or hit the poses, the table, or refer to the table to determine our electron geometry or molecular geometry. Electron geometry includes lone pairs. Molecular geometry excludes lone pairs. So this would be our shape including lone pairs. Our options are linear, trigonal planar, and tetrahedral. For electron geometry. For our molecular geometry, our options are still linear, trigonal planar, and tetrahedral, but we also have options of bent and trigonal pyramidal. Give you some more time to finish your writing. And we'll do some examples. What is the approximate shape of each of these molecules? For PCl3, I'm not taking crazy pills today. Nice. Step 1, draw the correct Lewis structure. I don't expect you to come up with it that fast. But that would be our correct Lewis structure for PCl3. Think about what's the shape going to be for that. And I believe this is the electron geometry, not the electron geometry, the Lewis structure for NOF with nitrogen as the central atom. For us, I would also expect us to come up with a resonance structure, but it's secretly the top one that's correct. All right, what do we think for the shape for PCl3? Trigonal what? Planar? Pyramidal? One, both. How many electron groups do we have on phosphorus? We've got 4. 4 electron groups. So what would our electron geometry be? Our 4 shape is tetrahedral. So if we're coming up with the molecular geometry, what we do, we hit the 4 shape. And how many lone pairs do we have? 1 lone pair, get rid of one of the groups. Any one will do. And now the 3 groups that we've got left, right, we started here, we got rid of one of the groups. Is this in the same plane as my other 2? No. It's out of the plane. That makes it pyramidal. This is 3 bonds, 1 lone pair. We poof away the lone pair when we're hitting our pose. Or we find it in the table. This is trigonal pyramidal. And what about for NOF, this thing? How many electron groups do we have? How many separate groups do we have on nitrogen? Double bond counts as 1. It's 3. 1, 2, 3. So we've got 3 electron groups. What would that shape be? What would that electron geometry be? Trigonal planar. That one is flat. We've got 2 bonding groups. We've got 1 lone pair. So we hit our pose. We hit our Y from the YMCA. We hit our diving into the swimming pool from a weird stance. Either way, we've got 1 lone pair. We get rid of that lone pair. And this shape, my arm and my leg from the YMCA pose, it's not straight up in the air, right? It's out to the side. So it wouldn't be linear, it would be bent. Or you just look it up in the table. So bent and trigonal pyramidal. Any questions about coming up with these shapes? Okay, over the break, at some point, please try to come up with the molecular geometry for the sulfite ion. This is where we'll be starting when we come back on Tuesday.